So first we're going to talk about some vocabulary, some different types of points that you might see and what it means. A critical point is a point where f prime of x equals 0 or undefined. So this point here is a critical point because the slope is 0. This point is a critical point because the slope is 0. This point is a critical point because the slope is 0. Although this point is important to us, it is not a critical point because for it to be critical, the slope has to be 0 or undefined. It is not 0 or undefined at that point. So points of inflection could be a critical point, but do not have to be a critical point. A relative local minimum, you might see the words relative or local, either one, but that's basically just a minimum on the graph. That's a minimum. Normally it's talking about the y value. If it says where is it, then it's going to be wanting the x value. If it says what is it, it's going to be wanting the actual y value, like how high or low it is. A relative minimum could also be a place where the slope is undefined, so that could be a minimum as well. If it were a graph that didn't go on forever, like these go on forever, but if it were a graph that maybe was a square root function or something like that, that could also be a local minimum because it's smaller than the points around it. Relative local maximum, similar to the minimum, it's just places on the graph where there's a maximum. Again, it could be a place where the slope is undefined. And if it kept going on that side but not on this side, that would be a maximum, that would be a minimum. And again, if it says where is it, it wants the x value. If it says what is it, it wants the y value. A stationary point is a place where the derivative is 0, 0 only. So sharp points are not stationary. Stationaries are only places where the slope is 0. Inflection points are places where concavity changes. Now, we do have to be careful. I told you in class about where the derivative is 0. It could be of an inflection point. It doesn't mean it's an inflection point. That's one possibility. But an inflection point is where concavity changes. This is possibly also true, but concavity has to change. And I can give you some examples that we'll look at later where the second derivative is 0 at a place, but concavity doesn't change, so it's not a point of inflection. So it has to change from up to down or down to up. And so it's dealing with that second derivative, meaning that second derivative could be undefined also at a place. But as long as concavity changes, second derivative changing from positive to negative, then it could be an inflection point. As far as the graph of those, it's hard to tell. I know when you have something like this that there's an inflection point, but sometimes it's hard to tell, but you would just be looking at concavity until I show you some other ways to do that. Absolute or global minimum, you might see both of those words. That's talking about on the whole entire graph. So let's say you have something like this. This one has a global or absolute max there. And there's no absolute min since the graph keeps going on forever on both ends. The next one was maximum, so I'm just kind of showing you all together what it would be. This would be a local maximum, this would be a local minimum, but they are not absolute because they are not higher or lower than the entire graph. So that's the reason that's a max and there's no absolute min. Alright, so let's talk about how we actually find some things without just graphing it. I realize you could graph this in the calculator, but on the AP test, this is not the kind of problem where they're just going to say graph this on your calculator and find the answer. It's going to be problems where you don't graph them. So I want to figure out where the maxes and mins are. And the way that you can figure it out is by where it changes from increasing to decreasing or decreasing to increasing. So I'll show you that. First, you're going to find the derivative. You're going to set it equal to 0 and solve. You get x is 4. So we're going to make a number line. Once you find the derivative, set it equal to 0, solve for the number, you're going to make a number line. Your number line is always going to be dealing with what derivative that you looked at. Like we're doing the first derivative, so we're looking at the first derivative. And you're going to pick numbers in each of those places, plug them into the first derivative, and figure out if you get positive or negative. So if I plug in a 0 into that, 2x minus 8, I get a negative. If I plug a 10 into 2x minus 8, I get a positive. And so what this tells me is that f of x decreases until I get to 4, then it increases. So thinking about decreasing and then increasing, decreasing and then increasing, that means there must be a minimum at x equals 4. Now, on all of these problems, when you say the answer, you have to have a reason. So there's a min at x equals 4 because f prime of x changes from negative to positive. There's no maximums. A maximum would mean that f prime of x would change from positive to negative. Because if f prime changed from positive to negative, then f of x would be increasing and then decreasing, which would indicate a maximum. And there's not one of those in this particular problem. Alright, here's another one. And on this one, I want to find where f of x increases or decreases. Now the good thing on this problem is that I've already found the derivative for you. It doesn't matter what the original equation is on this problem because the important part is figuring out where increasing and decreasing is. So you take the first derivative, you set both the top equal to 0 and the bottom equal to 0 because that helps you find all the critical points. We get x is 2 and we get x is negative 3. We make a number line. We're dealing with f prime, so we're thinking about plugging numbers into the derivative. So let's plug a 0 in. I would get a negative, so negative between negative 3 and 2. Plug a number bigger than 2, maybe 3, into x. So that would be a positive on top and a positive on the bottom. Maybe let's plug in a negative 5. It'd be negative on top, negative on bottom, still positive. So what this tells me is that f of x increases from negative infinity to negative 3 and from 2 to infinity because I know that f of x increasing means that f prime of x is positive. Also, f of x decreases from negative 3 to 2 because f prime of x is negative. Now, the problem doesn't ask you about maxes and mins, but I just want to show you this since there's more than one going on in this problem. There is a max at x equals 3 and a min at x equals 2 because we have a graph that is increasing and then decreasing, so that indicates a max. Then we have a graph that is decreasing and then increasing, so that indicates a max. Remember that the plus, negative, plus is dealing with the slope, so we're saying a positive slope and then a negative slope and then a positive slope. So it didn't ask that, but I wanted to show you that anyway. Okay, this problem says find the POIs. POIs are points of inflection. That's just a symbol for that. You can call it an inflection point or point of inflection. I know that points of inflection deal with the second derivative. So we're going to find the second derivative. The first derivative is 1 minus or plus sine of x. And then the second derivative is cosine of x. So the second derivative is cosine of x. Because I'm dealing with points of inflection, I want to start with where cosine of x is equal to 0. and I want to think about my number line. And we're just going to do this from 0 to 2 pi. That way we don't have to think about the whole entire graph. So remember that I think about these 4 points. This is 1, 0, this is 0, 1, and so on. And cosine deals with the x value, so I'm looking for places where the x value is 0. That would be at pi over 2 and at 3 pi over 2. So we're going to put pi over 2 and 3 pi over 2 on our number line. And I'm going to put 0 and 2 pi because I know I'm not going to go past that. So I'm going to start off with picking a number between 0 and pi over 2. Well, that's talking about the first quadrant. I know that cosine would be positive because everything's positive in the first quadrant. Then I'm going to pick a number between pi over 2 and 3 pi over 2. And so that would be both of these sides. Well, I don't know what you remember about trig, but this was a special saying all students take classes, and that tells you what's positive in each quadrant. Well, sine is positive in this quadrant, tangent is positive in this quadrant. That means cosine is negative in both of those quadrants. And then lastly, cosine is positive in this quadrant. Now, you could actually plug in numbers into cosine if you want to, but I just wanted to sort of think about the unit circle and relate it to show you where those positives and negatives come from. Now, what that tells me is that there's a point of inflection at pi over 2 and at 3 pi over 2 because I've plugged those things into the second derivative, and the second derivative is going from concave up to concave down to concave up. And because concavity is changing at each of those places, then there's a point of inflection at each of those. So POI at x equals pi over 2 and 3 pi over 2. And my reason is that f double prime of x changes sign. If it would have been positive, positive, negative, then there wouldn't have been a point of inflection at pi over 2 because the second derivative would not change sign. Remember, the second derivative positive means that the equation is concave up in that category. And second derivative negative means concave down in that category. Alright, this problem, we're going to find any maxes and mins that the graph may have, that f of x may have. So all of this is dealing with what's going on with f of x. Our maxes and mins deal with the first derivative, so let's find the first derivative. It'd be 2/3 x squared minus 16, subtract 1 on the power, then multiply by the derivative of the inside. We're going to set that equal to 0. And when we set that equal to 0, basically we're setting each part equal to 0. So if we solve that, we get plus or minus 4, and we get 0. So we're going to put all of that on a number line. We're dealing with the first derivative, so we're going to plug in numbers into the first derivative to see if you get positive or negative. So let's plug in a 1. Alright, if I plug in a 1 here, that's a negative. This is a cube root and it's on the bottom, so it'd still be negative. Plug in 1 here, that's positive, so I've got positive times a negative, so that would be negative for the 1. Alright, between -4 and 0, let's plug in a -1. So -1 plugged in here is still negative. Negative plugged in here is negative. And so that makes that a positive. Plug in a 5. 5 plugged in here is positive and positive here, so that would be positive. And lastly, a -5, -5 in here is positive, -5 here is negative, so that would be negative. Now, this means that f of x decreases, then increases, then decreases, and then increases. So decreases, increases, decreases, increases. That means that we have a minimum at -4, a maximum at 0, and a minimum at 4. So now we just need to describe that X equals -4 and 4 are minimums because y prime changes negative to positive. X equals 0 is a maximum because y prime changes positive to negative. You need to sort of start memorizing those rules. Okay, let's deal with concavity. Concavity means where is this graph concave up or concave down. That deals with the second derivative, so I'm going to find the first derivative. Be e to the negative x squared times negative 2x. Now I'm going to find the second derivative. I have to use the product rule. First times the derivative of the second plus the second times the derivative of the first, which is e to the power times the derivative of the power. I can factor out e to the negative x squared, left with negative 2 plus 4x squared. Set each part equal to 0. So when I set this equal to 0, I'm going to add 2, divide by 4, and I know I'm doing this sort of without writing it all down, but you're going to get plus or minus square root of negative a half. Alright, plug in some values into the second derivative. For example, plug in 0 right there. I'm going to get e to the 0 and then times a negative, so that's negative. Square root of 1/2, you might have to figure out what square root of 1/2 is to plug it in, or just know it's 100 would be bigger, so plug in 100. You get a positive. Plug in negative 100, you still get a positive. So what this tells me is that the graph is concave up and then concave down and then concave up. So it's concave up. I think I'm going to write this on a new slide. It's concave up from negative infinity to negative square root of a half, and also square root of a half to infinity, because f double prime of x is positive. It's concave down from negative square root of a half to positive square root of a half, because f double prime of x is negative. Now, if it would have asked about points of inflection, there would be points of inflection at both plus or minus square root of half, because concavity changes or because f double prime of x changes sign. Alright, here's two problems that I want you to try. Number 1, 2x to the third minus x squared. I want to know where that graph f of x is concave up or concave down. And number 2, y equals x to the fifth minus 5x. I want to know where that graph is increasing and decreasing.